Welcome to the first lecture in this analytics course. You might be sitting there thinking, why did I just buy a bunch of stats books for a class that's supposed to be about data analytics, or why do I need this course? So business is changing, right? So decisions used to be made intuitively, but we're really kind of moving away from that and moving more towards data-driven decisions. Because our competition is increasing, our environment has been tightened, and now we are expected to have greater efficiency standards. And so the shift is in response to how competitive that environment has been. Another thing to think about is that products have changed. They used to be very trade oriented. And now we're looking more at electronics and complex engineering. And once again, that efficiency in our production rates need to be much more attuned and managed. So, kind of think about our math being moving beyond science. Quality originally was the domain of the artesian um, and transferred over to the statistician in the early 1920s. And part of this was because many products were being destroyed when they were doing product testing. And so they were wanting to find a way to tell if one batch to the next was the same without completely destroying their product. And then also it became much greater accepted and highly adopted into business by the World War II, when companies were having to ration their resources and efficiency became much more important for the business to remain successful. We also saw a lot of that in the War Department for the UK and Ministry of Defense. Both of them used what's called operations research to kind of drive logistics and weapons design as well as the strategic defense configuration. So then it moved into business around maybe the 1970s, and so we started seeing a lot more operational research, and it moved beyond just that defense perspective. One of the groups at Western Electric in Japan was well known for using these new methods and embracing statistics. So why are you in this course is because companies are looking for individuals that can take a spreadsheet and do something more with it than just put the numbers in the squares. So what can you expect out of this course? So this course is going to be an application-oriented course where we get our feet wet and we start looking at the fundamentals of statistics. So one thing to keep in mind is reading about math is nice, but we only really learn math by doing math. So you will have some theoretical portions of the course where you're expected to read the book and answer some questions about that, but you also have application portions where you get to actually use the techniques and interpret the techniques, and then you also have some additional assignments where you will be reflecting on these topics and how it may impact you or already impacts you. But the bottom line is do your stats homework. It's going to be good for you. So think of all the millions of poor kids who go to bed without any statistics at all. So when we start about talking about analytics, this modern business environment is going to be driving that need for math-based decision making. And so this course is going to introduce you to basic statistics, forecasting, and quality control methods. It's going to prepare you for materials that you will encounter in subsequent courses, as well as within that idea or that realm of big data environment in business. So we have three main techniques within this field. We have descriptive analytics, which tells us what has happened, what's currently going on. Those are typically where you get those summary charts saying what the average is, or you're looking at a bar chart. It's going to tell you what has happened in the past. It's a description of what has happened. Then you have another area called predictive analytics. Sometimes it's also called inferential analytics. And so what that's going to do is you're going to use previous occurrences, previous data, and develop a mathematical model to be able to make some kind of prediction or maybe assess what the future impact is going to be if you change one of the variables. And then our third type is prescriptive analytics. So that's going to be a set of analytical techniques that's going to tell you what your best course of action will be. So When you take the data and you're looking at who you want to study, that population is going to encompass every single individual that could possibly be in that category that you want to investigate. We have two types of populations. We have a finite population and an infinite population. So a finite population is one where you can go through and absolutely count everyone who is, let's say we could say all registered voters in Denton County. So there is a definite list of people that are registered at this particular moment in time. And so that would make that a finite population. An infinite population would be all the fish in a lake. Okay. Or all the caribous in Australia. So that's a little bit more difficult to quantify exactly where those boundaries are. The other thing that we want to talk about is the census. So when you have a census study, that means that you are aiming to capture every individual within that population. So that's exactly what our government does every couple of years. We do a census, and the purpose of doing that census is so that our government can have a better idea of where the resources needs are of our population. Okay. We also have samples, right? So due to the problems with population level or census studies, it's often going to be more manageable to perform a study on a sample of your target population in order to then make inferences about that population. So, for example, think about when you sample something that you're cooking. You taste it, which would be an examination. And you take a small part of what you're cooking to get an idea of what that whole dish tastes like. But when you taste that spoonful of soup and you decide that that spoonful that you tasted isn't salty enough, we would call that exploratory analysis. Okay, you take your data, you look at what you have, you look at your graphs and distributions and whatnot. That's just exploring what you have. Then, if you generalize and conclude that your entire soup needs salt, that's going to be an inference. So that's you saying, okay, from this spoonful that I tasted, this spoonful doesn't have enough salt, therefore the whole pot of soup doesn't have enough salt. Okay? But in order for that inference to be valid, you need to really make sure that that sample is really representative of what's in your population. So in our soup example, what you would do is you would take your spoon and you would stir up your soup pretty thoroughly so that you get a pretty good distribution of the contents of the soup. And so if you just take it from the top of the pot, it's probably not going to be representative of that whole pot of soup. And so that would be one of the things that we have to think about when we are taking samples of our data. We also have something called sampling bias. So you want to look at the population of a certain type of individual, but you narrowed it down to the 40 people that you could approach. Well, if only 5 people that you approached actually give you responses, that response rate may be so low that it's not actually enough to justify saying that it's representative of your population. So for example, if I wanted to study all students at UNT and I only talked to 5 of you, due to the size of our population, I would definitely say that that is not a valid sample. And it would definitely be biased towards those students that I actually talked to. Another problem that can result in sampling bias is voluntary response. So this is when you have people that have very strong opinions about what you're asking. So go to Amazon, find the products that have 5 stars and 1 stars, right? Those would be your voluntary responses. So the people that are really, really happy with the product or the people that are really, really upset with the product, those are the ones that typically respond to products. Barring any kind of promotional incentive that companies have, most of the time that's a lot of what you see in customer comments is that very polar response. And then a convenient sample would be people that are easily acceptable to accessible to the researcher. So if I wanted to study something about the population of University of North Texas students and I sample students that are in my class. So that would be a convenient sample because you guys are people that I speak to regularly. going on with our basic definitions, we have our variables. So that's going to be a population or a sample characteristic that we want to measure. So any kind of measurement that you have on your observation. So let's kind of back it up a little bit. When I talk about an observation, that's going to be my set of everything I've collected on one individual. Okay, so if I have individual A and I have recorded that individual A is male and 37 years old. I have two variables now, right? I have the gender variable and I have the age variable for that one observation. A parameter is a measure that's going to be calculated from our population. So examples of parameters would be your population size, looking at all the observations that are possibly eligible to be in your target group that you want to study. Notice that we're going to represent that with a capital N. Capital N tells me how many people are in my entire group of people that are eligible for the study. And then we have our population mean, which is going to be the average of everybody that's eligible for the study. And the symbol for population mean is going to be the letter mu. Okay. And then we have another one called statistic. And so this is going to be a value, instead of calculating it on everyone in the population, a statistic is a value that we calculate based on the sample that we took. So two common statistics that we have are sample size and sample mean. So sample size is lowercase n, and that's the number of people who were eligible for the study, but these are the ones that I got responses from. That would be my sample size. And then the sample mean, which is going to be represented with X bar, is going to be the average of the people that I was able to get responses from. So going on with data types, we have discrete data and continuous data. Discrete data is going to be data that's only based on integers. So that's really something you can only get from counting. Continuous data, you can have any number value be a valid number for that. So for example, you're measuring, so 2.5 feet. Okay, so you can have fractions with your continuous data. So when we're looking at statistics, we also have our different levels, right? So when we're measuring things, we're looking at quantifying it a lot of times, but oftentimes we just code it with numbers because it's easier for the computer software to do what we need it to do. So there are 4 levels of measurement. The first one is nominal scale. So that means I may assign a number of 1, 0, 3, 5, whatnot to represent a particular trait. So for example, I could be using color, where I code 0 represents a green flower, a 1 represents a blue flower, and a 2 represents a red flower. So the numbers mathematically don't necessarily mean anything, but they are representative of a very specific trait. My ordinal scale, once again, can be a numerical value, and this is a case when that order is going to matter. Okay, and so, for example, we're looking at ranking observations. So during the Olympics, if you have first place and second place in the 100-meter dash versus first place and second place in the 800-meter race, the distance between the first and the second place winner may not be the same amount of time, but the first place winner still gets gold and the second place winner still gets silver. So that order matters, but the distance between my measurements don't tell me anything because it varies from one type of object that we're measuring to the next. The next level of measurement is what we call an interval scale. So now my order matters, and now the distance between my observations, the distance between 1 and 2, is going to be a set amount. Okay, but the big thing about the interval scale is that there is not a true 0 point. Okay, so the example that really comes to mind on this would be temperature. With the Fahrenheit scale, you can have negative Fahrenheit. Okay, so if I have the distance between 20 degree Fahrenheit and 30 degree Fahrenheit, that's going to be the same change in temperature as 40 degree Fahrenheit and 50 degree Fahrenheit. But if I have 200 Fahrenheit, 100 Fahrenheit is not half of that. Okay, because once again, we just have a scale and we have a 0 point that doesn't necessarily mean that we have absence of heat. Now, the ratio scale has all the characteristics of our interval scale. So the order matters. There's a definite space between my observations. But now I have a 0 point. And so going back to the temperature definition, that would be, or the example, that would be looking at the Kelvin scale. So 0 Kelvin is the point at which all motion stops. So you don't get negative Kelvin. Okay, so if I have 100 Kelvin and 200 Kelvin, now I have absolutely doubled my value. Okay, so here the big thing with ratio values is they're allowing us to construct meaningful fractions, meaningful relationships between the data. Another example of ratio scale would be looking at the number of customers served by a teller in a bank. So 20 customers served is going to be twice as many as 10 customers served. You don't have negative customers served, right? And so those are some things that even though when they're coded in the data sheet, they're coded numerically, they're treated very differently when we do our different types of analysis. So if we look at our flow chart here, we have numerical data being divided into types of data, quantitative and qualitative. And then we have our levels of measurement. So qualitative data can be nominal or ordinal. Nominal means I just assigned a number to it. It doesn't mean anything. Ordinal means I've assigned a number to it, and it definitely has some meaning that this is bigger than that, but the distance doesn't make a difference. With quantitative data, we have interval and ratio. Interval means that we can make meaningful differences, but we don't have a true 0 point. And with ratio, we have properties of our interval data, but now we have that true 0 point. And when we're looking at quantitative data, we can have discrete or continuous data, either of which can be interval or ratio data. So discrete is when you're counting. You have to have whole integer values. And then continuous can be any fraction of a number. So looking at our example, IQ scores of students at UNT. So that's a quantitative value. It's a discrete variable. And the distance between one IQ point to the next is going to be my interval value. But it's discrete because you don't have an IQ of 140.5. Okay, so that's why those are that way. And then if we're looking at the weights of 50 randomly selected students, so it's a weight, it's a measured value, so it's a quantitative value. So we're looking at the weights. You can have a fraction of a weight, so we're definitely going to say that that is continuous. Weight can have a 0 value, and it's actually meaningful, so we're going to say that that's a ratio variable. Another piece of data that might be collected is the region of the country that you live in. So east, west, north, and south. All of those numerical values, they mean something, but it's just a name. Okay, so this is going to be qualitative data. So since it's qualitative, it's not going to be eligible to be discrete or continuous. And since the numbers represent the names of our values that we're measuring, it's called nominal data. And then our last example is the number of students who graduated from UNT in each of the last 5 years. So number of something, that's quantitative. They're students. We can't have half a student, so that's going to be a discrete value. The number of students, 0 is a meaningful value, so that means that this is going to be ratio data. And then once again at the bottom we have a summary table of the different levels of measurement. So the order of the data is meaningful, applies to ordinal, interval, and ratio data. The difference between data values being meaningful is applicable to interval and ratio. And then the presence of a 0 point representing total absence is only showing up for your ratio data. So why do we collect data? We collect data so that we can compare it. So when we collect it, we divide our participants into treatment and control groups. And basically what happens is the control group either doesn't get any kind of treatment at all, or they get the existing treatment that everybody's already getting. And then the treatment group is going to get whatever's new. And the reason why we do this is so that we can see if there are any changes in the treatment group in comparison to that control group. And then we use statistics to quantify if that distance is big enough to care. And so we have explanatory response variables are going to be those that might affect your outcome or your response variable. And so we're just going to be looking at patterns in the data and the relationships to see if there's anything that any kind of conclusions that we can make. And so we have primarily two types of data collection. We have observational studies, which is just going to kind of look at what's so. Oftentimes those will be your surveys. And so they can provide evidence of naturally occurring associations between variables. But because it's just looking at one particular point in time, it's not able to give you that cause and effect. But an experiment can do that. Okay. And in an experiment, the researchers are going to randomly assign participants into the control group and the experimental group, in order to establish if there are causal connections between that explanatory and the response variable. Some principles of our experimental design: you've got to have some kind of control. You have to have a point of reference for comparison. You need to have your participants randomly selected. Going back to our different sampling types and sampling bias, your goal is to minimize that sampling bias so that your responses and conclusions are more likely to be generalizable to the population. You want to be able to replicate it. So you want to have enough people in your study so that it gives you a greater chance of it being representative of your population, so that if you were to do the study again, you would get similar results. And then another thing that we can do is blocking. So if you have some variables that are known or suspected to affect that response variable, you're first going to group your subjects into what we call blocks based on those variables, and then we're going to randomize the cases within each of the blocks into treatment and control groups. So as an example, if we're looking at an energy gel, treatment group is going to be those that take the energy gel, and the control group are those that don't get it. If we suspect that the energy gel might affect our pro and amateur athletes differently, we're going to have to use a blocking approach. So we're going to put our amateur athletes in one group, our pro athletes in another group, and then divide those two groups into control and treatment groups so that we can get an equal representation of those different groups within those different samples within our groups. And so blocking is very similar to stratifying, except we use it in experimental settings when randomly assigning it could potentially give us an imbalance of a trait. More terminology. We've got a placebo, which is going to be that fake treatment. Oftentimes you hear it as, giving the sugar pill. You're doing something different, but it's not really supposed to actually do anything. And so that placebo effect is when you're saying, okay, I'm taking a pill, so therefore I must feel better. And then blinding is when the participants in the study don't know if they're in the control group or the treatment group. And then double blind is when both the participants and the experimenters don't know which group the participant belongs to. And we do that so that the people administering the treatment or whatnot don't impose an additional bias of their own, saying, okay, I know you're getting the placebo, so I'm not going to pay attention, or I know you're getting the treatment and I'm going to look for any minute change so that I can prove that my treatment worked. And so the double blind kind of helps to eliminate that bias. And then finally we come to association and causation. Okay, so when I have two variables that show some kind of connection to each other, we say that they're associated. Now, you can have associated variables and have one of them depend on the other one. And so we call those dependent variables. And if we have two variables are not associated, there's no evident connection between the two, we say that they're independent of each other. So in general, just because I have an association doesn't mean I have a causation.